Hello students, welcome you all. Now in my previous lecture of alkyl halides, I had told you about the nucleophile and base, or difference between nucleophile and base, difference between nucleophilicity, basicity, and the concept of leaving group. Now in this lecture, I will start the nucleophilic substitution reaction with SN2 reaction. So if I write this nucleophilic substitution reaction, the general nucleophilic substitution reaction, then suppose this is the any substrate molecule, and when a nucleophile attacks over this substrate molecule, then so it will attack over the electron deficient center, as these nucleophiles are electron rich species. So it will donate its electron pair to this electron deficient center, and this group it will leave out, which is called as the leaving group. So what would be formed? This R1, this is R2, R3, and here this nucleophile is substituted, and this X, that is being leave out. So this is leave out. So this is called as the leaving group. This is our nucleophilic substitution product. This is our substrate molecule. This is the substrate molecule, and this is our nucleophile. This is the nucleophile. Okay, so this is the general nucleophilic substitution reaction. Now this SN2 reaction. Now let's start with the SN2 reactions. So SN2 reaction means this substitution nucleophilic bimolecular. 2 stands for this bimolecular. So substitution nucleophilic bimolecular, or we can say this is a bimolecular nucleophilic substitution reactions. So what are the main features of this nucleophilic substitution reaction? Then I will tell you the detail with the examples. So what are the main features of this nucleophilic substitution reaction? So first let me write some main features. So one of the thing, this reaction, this nucleophilic substitution reaction, this is the first order, this is one step reaction. This is one step and second order reaction. So this is one step reaction. One step reaction, or we can say this is a concerted reaction. This is a concerted reaction. Concerted reaction means when bond breaking and bond formation, it occurs in a single step with the formation of one of the transition state. So here that is bond breaking and bond formation, occurs in a single step. With the formation of transition state, with the formation of one transition state, only one transition state that would be formed. So if I see the energy profile diagram for this, that would be something like this, that I will see later on. So if this is reactant, this would be the product, and only one transition state is formed. So such type of reaction which is going only in one step reaction with the formation of one transition state, this is the one of the feature of a nucleophilic substitution reaction. Now second thing about this nucleophilic substitution reaction, that it follows second order kinetics. Already I have told you in my previous lecture that nucleophilic substitution reactions, okay, this is the kinetic concept. Means we talk about the rate of reaction, how much fast the reaction is. or how much slow the reaction is. So it follows the second order kinetics, and if it follows the second order kinetics, then rate, it depends upon the two reactant molecule, the concentration of two reactant molecule. If I write the rate equation for this, then this rate is equal to K constant, and the concentration of nucleophile and the concentration of, as well as the concentration of substrate molecule. So the rate depends upon the concentration of nucleophile as the concentration of substrate molecule. So I will tell you little more detail with the example later on. Okay, so it follows the second order kinetics. It follows the second order kinetics. Now if I about the substrate molecule, what kind of substrate molecule should be there for the SN2 reaction? So the reactivity of this substrate, the order of reactivity of substrate for SN2 reaction, reactivity of substrate for SN2 reaction is the primary, or more than this primary, the reactivity order is methyl halide. Okay, methyl halide is more reactive than the primary alkyl halide, then the secondary alkyl halide, then the tertiary alkyl halide. So tertiary alkyl halide is the least reactive, or it will not react. It will not react with the any nucleophile, whereas this methyl halide is the most reactive one, then this one, then this one. So what are the factors why this is more reactive, that I will discuss with the examples. Now another thing that this rate of this nucleophilic substitution reaction, it depends upon some factors. So the rate of reaction depends upon the steric factor, that is the size, steric factor, as well as the medium in which the reaction is carried out. That is, the medium, either it may be the polar protic solvent, or it may be the polar aprotic solvent. Polar protic solvent or polar aprotic solvent. So now in my previous lecture, I have already discussed about the polar protic solvents, what are polar protic solvent and what are polar aprotic solvents. Polar protic solvent means which forms the hydrogen bonding, containing the hydrogen atom and which is involved in the hydrogen bonding. Polar aprotic solvent which contains the hydrogen atom, no doubt, but it is not involved in any hydrogen bonding. So that is called as a polar protic solvent and polar. But solvent should be the polar one. For nucleophilic substitution reaction, the solvent should be the polar one. Another important feature of this reaction, so it depends upon this one, steric factor as well as the medium. Another important feature of this reaction, that this nucleophile, in case of SN2 reaction, nucleophile attacks from the backside of this leaving group. So nucleophile attacks from the backside, not the front side of this leaving group. So nucleophile attacks from the backside, and if it attacks from the backside, then what will happen? Inversion of configuration will occur. So, and that is also called as the Walden inversion. So nucleophile attacks from back side of leaving group, or we can say opposite side of leaving group, to give inversion product or inverted product. Configuration is changed, and this is called as a Walden inversion. It is also called as the Walden inversion. It is also called as the Walden inversion. Okay, so let's understand these features with the help of examples. So suppose if I have some alkyl halide, and nucleophile methyl bromide. So methyl bromide in presence of this hydroxide ion as a nucleophile. So this is our nucleophile and this is the substrate molecule. Okay, so this nucleophile, it will attack over the electrophilic center. So this carbon having the partial positive charge and this bromide ion having the partial negative charge, and it will form a nucleophilic substitution product, that is methyl alcohol, and plus this bromide ion, this will leave out. This bromide ion will leave out. Okay, so in this reaction, what I told you, such nucleophilic substitution reaction, these are they occur in one step. They occur in one step with the formation of a transition state, or we can say this is a concerted reaction. So the transition state which is formed, we can write the transition state as or suppose I write so this is a concerted step where bond breaking and bond formation, it occurs in a during the same time. Okay, so this will have the partial negative charge. So this is the transition state which is formed. Now if you will see, then this methyl bromide, it is sp3 hybridized. This carbon has sp3 hybridization and it is a tetrahedral in shape. This is tetrahedral in shape, and the transition state which is formed here, so this is a 5 coordinated. So this tetrahedral methyl bromide is a tetrahedral shape which is 4 coordinated. Here this is 5 coordinated. So this transition state, it is a trigonal bipyramidal shape. So shape of this transition state would be trigonal bipyramidal. Okay, so and finally the product which is formed is again sp3 hybridized. When this the bond between this carbon and this bromine completely breaks, and the bond between this carbon and this hydroxide ion, that would be formed. So the attack of this hydroxide ion, it will take from the back side. So what I told you in the features of this SN2 reaction, the nucleophile attacks over the substrate molecule from the back side. So when the attacks occur from the back side, then inversion of configuration will take place, or we can say if the substrate is having the R configuration, then the product, nucleophilic substitution product, will have the S configuration, and suppose it has the S configuration, and product will have the R configuration. So if we see the stereochemistry, and suppose if we have the substrate molecule, if I have substrate molecule like suppose this is secondary alkyl halide. Suppose if I have the secondary alkyl halide, or this is 2-bromo-butane. This is 2-bromo-butane. and if we see this configuration for this, then if I want to decide whether it is the R configuration or this S configuration, then first of all we should give the priority to the groups. So this bromine, that should be given priority number 1, and this ethyl group that should be given the priority number 2, and this methyl group that should be given the priority number 3. Whereas the hydrogen which is present over this carbon, this is the chiral carbon center, so hydrogen which is present over here, that is having it is away from the observer. So we can also otherwise, for understanding, we can write the hydrogen is away from us. So if we see the whether it is from first to third, from first, second, third, so we see that it is going from it is in clockwise direction. That's why it has the R configuration. Okay, if it is in clockwise direction, then R. If it is in anti-clockwise direction, then it would be S. So it is having the R configuration. So one of the condition for deciding whether it is R or S, that hydrogen, the last priority group, the lowest priority group, should be away from us always. So now what we will get the substitution product? So this OH that would be substituted here, and that should attack from the back side. So as we can see, this bromide ion, or which is the leaving group is towards us. Okay, leaving groups is towards us. That's why the bromide ion should attack from the back side, that is away from this us. So what we can do, it means the bromide ion will attack from this side, means the side where the hydrogen is present, which is present away from us. So it means what should be the product? The product that we should write, the bromide ion, and that should be replaced here, and in place of bromide ion we should write the hydroxide ion. So as you can see, now first of all the bromide ion was towards us. Now this hydroxide ion, which has replaced this bromide ion, is away from us. Why? Because always the nucleophile attacks from the back side. Now if you want to decide the configuration of this, now again we should see whether it is R or S. Then this oxygen OH group, it is giving the first priority. Now this ethyl group, we should give it the second priority. Methyl group, that should be given the priority number 3rd. Now if we see from first, second, third, again it is going into the clockwise direction. So clockwise direction, but here the least priority group, the lowest priority group, which is hydrogen, this hydrogen is not away from us, it is towards us. The hydrogen is towards us. That's why in such case, if we are getting the R configuration, then configuration should be reversed, that is S, because the hydrogen is towards us, not the away from us. So that's why we should write the configuration S2 hydroxy or we can say 2-butanol, or we can say S2-butanol. So this would be the product, and this bromide ion, it will leave out. So we should remember that in SN2 reaction, the hydroxide ion always attack from the back side, and we get the product which is the inversion product we get. So here we get the inversion product. Inversion of configuration takes place. Okay, now let's see some examples. So as I told, the order of reactivity of alkyl halide for SN2 reaction, the order of reactivity is methyl bromide react much faster in comparison to the primary alkyl halide, secondary alkyl halide, and then tertiary alkyl halide. So we can say that tertiary alkyl halide is gives least means the the rate of this substitution reaction for tertiary alkyl halide is very less, very low in comparison to the methyl bromide or primary alkyl halide. So if we see the rate, so suppose I am writing this methyl bromide, and so if it is substituted by, suppose, cyanide as a nucleophile, so what you will get? CH3 methyl cyanide. And suppose again this attacks over the one of the primary alkyl halide, suppose it is propyl bromide, and it is giving the, and again now if we are having the secondary alkyl halide, secondary butyl bromide, then it will give you the substitution product where this cyanide CN group, where this CN group will attack from the back side. That's why the product that should be written, that should be the inversion product. So that's why I have writing this substitution, and we are writing this nucleophile in a dash form. Okay, in the same way, suppose if we have a tertiary alkyl halide, suppose if we have a tertiary alkyl halide, so this is our tertiary alkyl halide, and for this we can write the substitution product. So the rate of this nucleophilic substitution reaction, so the rate of substitution reaction, suppose it is 1000, then the rate of substitution reaction that for this will be only 10, and for this the rate of substitution reaction this will be 1, and for this tertiary alkyl halide, the rate of substitution reaction is very less, and which is 0.001 in comparison to the methyl bromide, or in comparison to this primary alkyl halide. So we can see that the rate of substitution reaction for tertiary alkyl halide is very less. So that's why usually this tertiary alkyl halide doesn't give the SN2 reactions. Now let's see one of the general reaction. If I write the general reaction, then suppose this is our primary alkyl halide, and this primary alkyl halide, it can react with various nucleophile, and this nucleophile that will become substituted. So nucleophile is substituted, and we are getting this bromide ion as a leaving group. In the same way, suppose nucleophile, if I take the secondary alkyl halide, then the substitution product that we are getting, so inversion product we will get. So nucleophile, after substitution, it will give you the inversion product, and again this bromide ion, this will leave out. So here various nucleophiles we can write. Suppose I am writing here the general nucleophilic substitution reaction. So nucleophile may be either hydroxide ion may act as a nucleophile, or we can say this amide ion can act as a nucleophile. Amide ion may act as a nucleophile, or this alkoxide ion may act as a nucleophile, or bisulfite ion may act as a nucleophile here. Similarly, RS, so it may act as a nucleophile, or cyanide ion may act as a nucleophile. Okay, cyanide ion may act as a nucleophile, or this azide ion may act as. So we can write, if these nucleophiles are present, then we can write the substitution product either for the primary alkyl halide or for the secondary alkyl halide. In the same way, suppose if we have acetate ion may also act as a nucleophile. Similarly, acetylide ion may also act as a nucleophile. So these are the different nucleophiles. Now suppose, let's take one of the example. Now suppose if we have a substrate molecule, if we are having the substrate molecule, this is one of the substrate molecule, and this is the, suppose, another substrate molecule, and next one is, this is the another substrate molecule, here bromide. Now out of these three substrate molecule, which will react faster, which will give the faster nucleophilic substitution reaction? Okay, so we have to decide which will give the faster nucleophilic substitution reaction in these three alkyl halides. And these, if we see, then all these three, these alkyl halides, these are the secondary alkyl halide. This is secondary alkyl halide because this carbon is attached to these two carbon. Here also this is secondary alkyl halide because this carbon is attached to these two carbon. This is also secondary alkyl halide. This carbon is attached to these two carbon. Because all three are secondary alkyl halide, so that's why we should see the carbon which is present in the neighbor. Now if we see, then this carbon which is present in the neighbor of this carbon, then this is the tertiary carbon, this carbon is the tertiary carbon, this carbon is secondary carbon, and this carbon is the primary carbon. So what I told you, the nucleophilic substitution, it depends upon the steric factor also, or the size of the substrate we can say, or the size of the nucleophile also. So in this case, this substrate molecule is more sterically hindered, so that due to the presence of this bulky tertiary butyl group, here this tertiary butyl group is present, here we are this isopropyl group is present, here simply the methyl group is present. So that's why due to the presence of a tertiary butyl group, the rate of attack of nucleophile over this carbon center, that will be hindered one. So that's why this will give me the slow nucleophilic substitution in comparison to this and this. So rate of nucleophilic substitution reaction will be something like this. In the same way, suppose I take another example. If I am having the suppose this is vinyl bromide, and we are having this is allyl halide. So this is allyl halide, this is allyl carbon, allylic carbon, and this is the vinylic carbon. So bromine is present at the vinylic carbon. Here the bromine is present over the allylic carbon center. Okay, so that's why which one will give the nucleophilic substitution? Either this one, or the both one. So in this case, this vinyl bromide will not give the nucleophilic substitution reaction, whereas this allyl bromide can give the substitution reaction. So what I told you in the example, the substrate molecule, that should be sp3 hybridized. So if you see here, this bromine atom is attached to the sp2 hybridized center. So this carbon is sp2 hybridized center, but in case of, because as this is sp2 hybridized center, that's why this carbon is highly electronegative. So due to this electronegative carbon, and this electronegative, this bromine, so it will, due to the presence of this electronegative carbon atom, this will not give the nucleophilic substitution product, whereas here the substitution will take place at this carbon center, and this carbon center, this is the sp3 hybridized carbon center. So that's why this can give the substitution product. In the same way, suppose I write, suppose if I am having the so this is one of the cyclohexane, methyl cyclohexane, means one of the this bromine atom is present over the cyclohexane, and one of the methyl group is also present over here. Now in this case, if we are having the nucleophile, then where the nucleophile will attack, no doubt their bromine will get substituted. This bromine can be substituted because this carbon center is sp3 hybridized carbon center. So this can be substituted. This may be substituted. Okay, but what will happen? As I have told you, the hydroxide ion will always attack from the back side. It will not attack from the axial side. So this one is the axial side of the cyclohexane, and where this is the equatorial side. So nucleophile will never attack at the same axial side. The nucleophile should attack from the back side, that is the equatorial side. So the product for this would be this one. So here the bromine will come at this center, at this equatorial position. In the same way, suppose if I am having aryl bromide. Suppose if I am having this aryl bromide and this bromine is not directly attached to this benzene. So suppose the bromine is present at this carbon. So which one will get can go the nucleophilic substitution reaction? Now if you see, this carbon center is sp2 hybridized center, so that's why the bromine cannot be substituted by any nucleophile. Okay, whereas this carbon center is sp3 hybridized center, that's why the bromine can be substituted by any nucleophile. Okay, so these are some of the examples. Now overall, if you will see, then let's summarize this SN2 reactions. So what are the factors? Which affect the rate of nucleophilic substitution reaction, rate of this SN2 reactions? So factors affecting the SN2 reactions. So one of the factors which affect the substitution reaction is, already I have told you, substrate. If you see then about this substrate, and what type of substrate favors the SN2 reaction? Methyl halide favors the rate of substitution of methyl bromide or methyl halide is faster in comparison to the primary alkyl halide, in comparison to secondary alkyl halide, and in comparison to the tertiary alkyl halide. In the same way, suppose if we see the leaving group, or suppose let's see for the nucleophile. Okay, so nucleophile, if we see the nucleophile, that strong nucleophile favors the SN2 reaction. In presence of a strong nucleophile, the nucleophilic substitution reaction would be faster. So stronger nucleophile favors SN2 reaction. And what I told you, according to this rate law, the rate for this SN2 reaction, it depends upon the substrate as well as depends upon the nucleophile. It means if we increase the concentration of substrate, if we are increasing the concentration of substrate molecule, then rate also increases. If you are increasing the concentration of substrate molecule, rate increases. As well as if we are increasing the concentration of nucleophile, then also the rate of reaction also increases. Means if we doubles the concentration of nucleophile, rate of SN2 reaction will increase. If we double the concentration of substrate molecule, then rate of SN2 reaction will also become double. And suppose if we double the concentration of nucleophile and if we double the concentration of substrate also, then rate of SN2 reaction will become the 4 times. Okay. In the same way, if we triple the rate of, triple the concentration of nucleophile, then rate of the SN2 reaction will become the 3 times, like this. Okay. So, and for this, So as the concentration increases, so what we can write, as the concentration of nucleophile increases, if the concentration of nucleophile increases, then rate of SN2 reaction also increases. Rate of SN2 also increases. Okay. Now third thing, if we have also, if you see the nucleophile, stronger nucleophile means if the nucleophile, negative charge nucleophile gives faster nucleophilic substitution reaction. So suppose if we have the OH minus, then this gives the faster nucleophilic substitution reaction in comparison to the water. Similarly, if we have suppose amide ion, this will give the faster rate of substitution reaction in comparison to the ammonia, and so on. And so on means if the negative charge is coming over the nucleophile, then the reaction will become faster, because as the electron density over this nucleophile is higher in comparison to this, so it means it can give their electron, it can donate the electron pair much more easier in comparison to this. Now third factor is the steric factor or size. Steric factor, and if we see the size of nucleophile. So as the size of nucleophile increases, then it creates the hindrance during the attack. It can create the hindrance during attack. So smaller nucleophile can easily attack over the substrate molecule in comparison to the bulkier nucleophile. So bulky nucleophile creates the steric hindrance. So for example, suppose if we have ammonia as a nucleophile, and if we have this tertiary amine as a nucleophile. So this tertiary amine is much bulkier nucleophile. So that's why no doubt this will give the faster rate of SN2 reaction in comparison to this. Similarly, if we have the alkoxide ion, it is methoxide ion. This is ethoxide ion. This is isopropoxide ion, and this is the tertiary butoxide ion. So this tertiary butoxide ion is the bulkier one. So as this is bulkier, so that's why the rate of substitution reaction, this will be slow in this case. This is bulkier nucleophile. So the rate of substitution reaction, that should be fastest in case of methoxide ion in comparison to this ethoxide and propoxide and tertiary butoxide ion. Okay, so these are some of the factors. And next one is what I told you, the medium. What kind of medium that should be? If we see the medium, so whether the polar protic solvent or polar aprotic solvent, one thing is clear, that the SN2 reaction takes place in presence of polar solvent, not the non-polar solvent. So solvent should always be the polar solvent, because the substrate molecule or alkyl halide being the polar one, that can only be dissolved in some polar solvent. So it needs this polar medium. The alkyl halide always needs the polar medium because this is the polar one. So one thing is clear, that the substitution reaction takes place in polar solvent. Now solvent, as I have already discussed in my previous lecture, that solvent may be polar protic solvent or it may be polar aprotic solvent. So this SN2 reaction favors or we can say the polar aprotic solvent. Polar aprotic solvent favors the SN2 reaction. Why? Because polar protic solvent, it forms the hydrogen bond with the nucleophile, and it forms a strong shell around the nucleophile. That's why polar aprotic solvent, for example, I already have told you acetone, it may be either acetone, it may be DMF, it may be DMSO, it may be acetonitrile, like this. So these solvent which does not form the hydrogen bond, these solvent does not form because it is polar aprotic solvent, and polar aprotic solvent does not form any hydrogen bond. So that's why they favors the SN2 reaction. Otherwise, if we have a polar protic solvent, then it may form the hydrogen bond with the nucleophile. It may form the hydrogen bond with this nucleophile. With these nucleophile, the hydrogen bond, the solvent will form a shell around itself. So that's why it cannot attack in that case. So that I have already discussed about this polar protic solvent and aprotic solvent for the nucleophilic substitution reaction. Okay, next, that is the leaving group. Already in my previous lecture I have told you the leaving group for nucleophilic substitution reaction, the leaving group should be the stronger leaving group or stable leaving group that should be formed. So stable leaving group means that should be the weak base or weak conjugate base. So what I told you the rule, weak conjugate bases are the strong leaving group. So weaker the conjugate base, better is the leaving group. Better is the leaving group. Okay. So for example, if we see, then leaving group, iodide ion is a good leaving group, iodide is a good leaving group, then bromide ion, then chloride ion, and then then hydroxide ion, like this. So hydroxide ion is a very poor leaving group. As this hydroxide ion is a very poor leaving group, that's why the substrate for nucleophilic SN2 reaction, nucleophilic substitution reaction, we don't take this alcohol. Alcohol doesn't undergo nucleophilic substitution reaction in normal condition. Okay, so these are some of the factors which affect the SN2 reaction. Now in my next lecture I will discuss the